I'm making this video for the question on page 112, number 8. So this is an advanced question. It's what we'd consider to be a standard of excellence question. And although there's nothing like this on your unit exam, this is a question you'll see occasionally in Physics 30 and higher level tests will often incorporate questions like this. So it's good practice for us to do it just so we're exposed to something that requires a little more than what we teach in class. So question number 8, it says that somebody in the Olympics, the long jumper, jumps a horizontal distance of 8.59 meters, and that the angle that they took off with was 23 degrees. 22 degrees, and that's all the information that's given to you in this question. So there's no initial vertical velocity or horizontal velocity, there's no time in the air or vertical displacement. That's the only information you're given. So obviously this person is going to go in a parabolic path like so, and if we approach this like we would any normal problem, we write down the horizontal elements, we write down the vertical elements, and then we go from there. So let's do that. Horizontally, we have the displacement. Do we have the velocity? No, we don't. Do we have the time? No, we don't. So horizontally, we're kind of stuck. Vertically, what do we have? Do we have the initial velocity? No. Do we have the displacement vertically? No. Do we have the time vertically? No. Do we have the acceleration due to gravity? Yes. That's the one thing we have. Do we have the final velocity? No. So we're at a big impasse here because we really have nothing. Now back to the initial velocity. Of course, you could say, oh, sorry, the final velocity. Remember that you can always say that the final velocity here is 0. So we'll just put all 0 just to cover our bases here. Okay, and then so we're looking over this information and we're thinking, oh, we are at an impasse here. We can't do anything for the horizontal components because we only have one piece of information. For the vertical component, you need 3 pieces of information to find the 4th. So you're kind of dead in the water at that point. But what do we say always unites the horizontal and the vertical components in projectile motion? And that is this thing. This, the time. The time always unites those two mutually independent components. Because we know that the time it's in the jumper is in the air horizontally is obviously exactly the same as the time vertically. So what our strategy in this question is to write an expression for the time horizontally, write an expression for the time vertically, set them equal to each other, and then see if we can go from there. So that's going to be our strategy. And just back to our diagram over here, what we're looking for, what they want is this, V. Right? You have the horizontal velocity, you have the vertical velocity, but what they want is the total velocity. In other words, the hypotenuse of this triangle. Okay, so let's go. Let's write expressions for the horizontal and vertical and see if we can come up with something that works. The horizontal is, and actually before we do that, let's separate this thing into its components. Okay, so the horizontal components, the horizontal velocity can be written as an expression, the cosine of 23 equals x adjacent over the hypotenuse, which is v. Okay, and we're going to solve that for x. X equals cosine 23 degrees v. Now remember that this x here, that's the horizontal velocity, so it's the same as this thing here. Okay, and therefore, when I write a statement for the horizontal velocity, remember the horizontal velocity is always always uses only this formula here. And if I want to write, sorry, another time, if I want to write an expression for the time, it's going to be the time equals the displacement over the velocity. I know the displacement, and I've just written an expression for the time, cosine 23v. So that's an expression because I've got two variables in this, don't I? I've got t equals 8.95 cosine 23v. All right, so I can't solve that. There's two unknowns. Let's go to the vertical component. What can we write? Which equation can we write that unites the vertical or that relates some of the vertical elements? And you could do it in many ways, but the easiest way to do it is just to use our standard acceleration formula. And the reason this is the easiest way to do it is because of this concept. If we know that the initial vertical velocity here is y, and the final, if we're talking about the entire motion of this whole thing, is going to be negative y. Now, you can use the zero. You can use the zero if you want, but then you get into other complicated things as now you've only doing the time for half of the flight. So it's easier because we're equating the two times, because we're saying the horizontal time equals the vertical time. It's easier to say that the initial vertical velocity is y, then right before it hits the ground, it's negative y. Therefore, this is the best formula, and when we solve this for t, we get this. And remember when we, okay, so first of all, we've got to write an expression. Let's go back to this guy right here. Write an expression for y, for the vertical velocity. And that would be, running out of room, that would be, let's just put it down here. That would be the sine of 23 degrees equals y over v, and therefore y, in other words, the initial vertical velocity equals 23, sine 23 times v. Okay, so that's the initial. Therefore, the final, if that's the vi, then the vf is going to equal negative sine 23 degrees v. Right? Just based on this right here. If this is the initial vertical velocity, when it comes down, it's the same velocity, it's just in the negative direction. Therefore, it's negative. Okay, so now we have two expressions for VF and VI, and we can plug them in to this formula here, giving us T. So first of all, we rearrange the formula for T. Then we plug those numbers in. T equals negative sine 23V minus sine 23V. Divided by negative 9.81. And this is good because now we have, I forgot the V here. It should be V right there. Now we have two expressions, both for time. Here's one. The horizontal time is the other. The vertical time, we know they must be equal to each other, and so we can just equate them, just like we did those advanced problems at the beginning of the unit, those advanced kinematics problems. So, actually, they were mostly uniform velocity. So we can just say that 8.59 over the cosine of 23 degrees V equals negative sine 23 degrees V minus sine 23 degrees V over negative 9.81. And that looks way more complicated than it really is, because this cosine 23 is just a decimal. I can just get out my calculator And I can say that the cosine of 23 equals 0.9205. So let's just say that, let's just call that 0.92. 0.92 V. And I can do the same to these, to this one here and this one here. Or another way to look at this is you can just say that this is negative sine 23V minus sine 23V is just negative 2 sine 23V, right? And then negative 2 times sine 23 negative 0.87 B over negative 9.81. Oh, not just oh yeah, B. Okay. So at this point, it looks a lot more friendly. Remember those B's, they're really just X's. If you're mathematically inclined, you want to replace everything with X, any unknown variable. You can cross multiply at this point. Cross multiply. And you're going to get 0.92 times 0.78. These negatives that cancel out is 0.7176. And you got a V times a V, so that's V squared equals 8.59 times 9.81 is 84.27. 84.27. Divide both sides by this little guy. That's going to give you V squared, so divided by 0.7176 equals 1017, and then square root both sides, and you get square root of the answer is 10.8. And that's it. That's what we were doing the whole time. We were just solving for V, and we've got the answer right there. There it is, V, right here. Okay, so as you can see, that's a pretty advanced problem. Takes a little thinking outside the box, but very solvable and very satisfying when you do solve it. So there it is. That's question 8 on page 112. We'll see you out there.